All right, it's about 5:30. I guess I should go ahead and get started. Jacob's already chatted me his first and last name. Everybody else, you can go ahead and do that as well. I wanted to point out that I'm about done posting your face-to-face test two exam grades. I've got about five students left that I'm still working on grading. I hope to have that finished tonight. If not, it'll be done first thing tomorrow, but I'm pretty sure I'll have it done tonight. I'll send out an email when it's done as well, so you don't have to keep checking back and forth because I'm going to send out an email about some comments I had, things I noticed that students are doing wrong, things I noticed that students are doing good, and also I need to explain how I'm grading it so y'all have some understanding of that. But anyways, when we last spoke, we were in chapter 9, which is on linear momentum, and we had completed all the linear momentum stuff. We hadn't done anything on the center of mass stuff. And once you have the center of mass stuff, you can start to talk about how we deal with actual physical bodies because what we were learning so far, we've been pretending like all the masses that we're dealing with are point particles because we don't yet have any understanding of the concepts of torque and stuff like that. And in order for you to really fully understand a physical body, you got to know not only where the force is, not only what the force is and what the direction of the force is, but where the force is applied relative to, for instance, the center of mass of the body. So we'll talk about that a little bit. As I also mentioned before, and I think I mentioned it in the email too. I want you guys to realize we are not covering the rocket propulsions section at the end of the chapter. It's an asterisk section, and that means it's normally optional for us. I am choosing it to be optional. I've tried to get them all those types of questions out of the homework as well as out of the practice tests, but there might still be some in there. I don't mind you reading it and learning how to use it and even doing it on a practice test or a regular homework assignment. It's just I'm not going to test you on it. So I just want to make sure everybody was clear on that. So let's go ahead and get started on the center of mass section and finishing up chapter 9. And maybe we'll jump into chapter 10 next. I think it's chapter 10 next. Am I even remember the numbers right? Yeah, I am. Woo! Yay me. All right, here we go. Anybody have any questions before we get started? You can type them in if you don't want to speak up, but you're, of course, also allowed to speak up anytime you want. Okay, it should come up any second now. So what I've done is I've went ahead and taken the time to write down the actual formulas that we'll be using for the center of mass. If you look at it, and if you have any experience, for instance, with seesaws, you know that whenever you put two kids on a seesaw, then if the two kids are roughly the same size, then you want to put them both roughly the same distance apart on the seesaw or the same distance from the rotation axis of the seesaw in each case, because in that case it turns out, I haven't learned about torque yet, but in that case it turns out that it actually can level out and then the seesaw can balance or whatever. Again, that's mostly if they're the same distance from the axis of rotation and have about the same mass. If, however, one has a much bigger mass, then you're going to put that one up there with a bit smaller of a distance from the axis than the other one. And that can sort of give you a motivation for seeing why the center of mass requires a calculation of each individual mass particle that makes up the thing times the distance from the let's say the y-axis, for instance. You can put the coordinate origin anywhere you want. You can put the y-axis pointing any direction you want. You can put the x-axis pointing any direction you want. But once you've done that, then if you want to find the center of mass of an object that's made up of n particles, then you have to take m1 and multiply that by its x1 coordinate, and then m2 and multiply it by its coordinate x2, and again keep on doing that up till you get to mn, and you're going to multiply it by its x coordinate xn. And then to make the units work as basically as the same units that it should be, because it's an X center of mass, it should have the units of X, not kilograms times meters, which is what the numerator has. So one way you can think about this denominator is just to make the units right. And it doesn't make any sense to divide by a particular mass. The only thing that makes sense is dividing by the sum of all the masses. So that's what the formula is for. This is the exact same formula, but written in that really short summation notation. Now, that's all well and good as long as you're dealing with point particles, or if you're dealing with discrete parts whose geometry allows you to know exactly where the center of mass of those things are, because these could be M1 could be an actual physical object as opposed to a point particle, but that physical object has a x coordinate of center of mass equal to x1, and its mass, or at least its fraction of the mass, would be m1. And the same thing with M2 here. That would be another section, which I'll explain to you later, in terms of breaking up shapes into various smaller shapes and then using the geometry of those smaller shapes to find their center of mass and stuff like that. So you can use this with, discrete objects as well, or excuse me, with continuous objects as well. But in that case, you're not doing point particles. You're doing whole chunks of matter and trying to compute the relative mass of that one chunk compared to the whole mass. But either way, that can be done. And then, as I said, if you want to assume that matter is actually continuous or smooth instead of the discrete particles that we actually have, atoms, then you can assume that the a certain volume or a certain space of the mass has a very small one for that matter, a very small space of the mass has a mass dm, and its location is x meters from the y-axis, and you integrate the x dm, and then you divide that by the integral of dm, and that'll give you the center of mass if the matter is continuous. In order to do that, you need to understand how do we go about getting dm. Well, dm can either be an object that's like one dimensional, for instance, like a bicycle spoke, or maybe even a broom handle if you're talking about some distances that are bigger than, let's say, a half an inch. Let's say if they're at least 10 times a half an inch, which would be about 5 inches. If you're talking about distances on the order of 5 inches or larger, then a broomstick would work just fine to assume it's a point or it's a one dimensional object. In that case, then you have a mass per unit length, lambda, times the differential length, dl. Or if you had a two-dimensional objects like a stop sign, for instance, then you would have the mass per unit area, sigma, which is obviously a quantity that would have units of like kilograms per square meter, and then that's multiplied by a differential area element. Or if it's a three-dimensional object, then you have a normal density that you're used to, which is rho, and that's measured in kilograms per cubic meter. And you get the mass, the dm, by multiplying that rho by dv, a differential volume element. So you've got to keep those in mind because we're going to use those same things next semester too in 242. Only we're going to be doing lambda as if it's a charge per unit length instead of a mass per unit length. We're going to do sigma as if it's a charge per unit area, and we're going to do rho as if it's a charge per unit volume. So it's the exact same stuff again. And we're going to use these exact same ones later in the next chapter. I think it's either next chapter or the one after that. When we go to calculate the moment of inertia, which is sort of something analogous to the mass of an object when you're trying to rotate it. It's not just the mass that depends on how hard it is to get something rotating. It's the mass and how that mass is distributed. For instance, if you want to spin a pencil like this, that's easy peasy because all the mass is really, really close. But if you want to spin a bicycle wheel, it's a little harder because some of the mass is out at the end of the spokes. And in fact, if you fill the tire up with lead shot instead of air, then the majority of the mass is out at the tire's edge, and therefore it's a lot higher moment of inertia. So the moment of inertia takes into account that distribution of mass. In fact, the only difference is the I moment of inertia is equal to the integral of r squared dm, where r is the distance from the rotation axis to the differential mass element. So that's an intro to the center of mass. And your book talks about that a little bit. You should read it and go along with what I just said here. I usually take a little bit more time deriving it, but I've discovered that students don't necessarily respond to the derivation as well until after they've worked problems. So sometimes it's just better for you to grab the problem, grab the actual formulas I give you, see how they work, and then after you get a little bit more mature with that, go back and reread why is that the formula, and then see if it makes any sense to you. So, one of the key aspects, and this is going to become relevant in the next subsection of this chapter, is for instance, if I were to, let's say, throw this pin, if I throw this pin, you learned in projectile motion that a pin or any object thrown would, of course, follow out a parabolic path. That's a parabolic path in X and Y, but also a parabolic path in Y and T. So, for instance, Y versus T gives you a parabola as well. Uh, that's all well and good, but when I throw a pin, you'll see it doing all this kind of stuff, and you'd be like, "Well, what part is actually making the shape of a parabola?" Well, it turns out if you look closely, like you filmed it and then you watched, you would see there's one part of this pin that in every slide and every time interval is the center of rotation of the pin, and all the other points are rotating around it. Well, it turns out that particular point that appears to be having everything rotate around it is the center of mass. So, what you're going to learn is when you deal with physical objects, you not only need to know the center of mass because that's going to do the stuff that acts like a point particle, but you also need to know like some vector that points from the center of mass to a particular particle or a particular end of the mass. And you might even need three of those types of vectors because it's a three-dimensional object just to locate all the boundaries of the matter in space. And your job would be to solve the physics problem, not only figure out where the center of mass is going to be at some time later, but what are the orientations of those one, two, or three vectors so that you know, for instance, when I throw this pin, when it hits the ground, is it going to hit the ground tip first? Is it going to land flat? Is it going to land tail first, or is it going to land somewhere like this or something like that? All of that can be done using the equations and stuff we've now learned, and we're going to continue to learn in chapters 10, and then 13 and 14 is sort of unrelated, or excuse me, 14 and 15 is somewhat unrelated, but it's an extension of the problems. So hopefully that helps you better understand center of mass. You can see figure 922. They show a actual what I would normally call a crescent wrench or an adjustable wrench. And what they're showing is that when you throw an adjustable wrench, it appears to rotate like that, but there's one spot on that wrench that continuously goes in a straight line, which seems like it's obeying Newton's laws of motion. The thing obeying Newton's laws of motion are obviously the center of mass of the object, but it turns out the ends or the vectors that point from the center of mass to those ends, they can be treated with Newton's laws of motion too, only they're slightly different versions of the laws, and you can use those in combination to figure out everything about, for instance, a crescent wrench when you throw it. So let's start off with example 914. So now that I have the center of mass formulas, I'm going to try to solve a problem specifically. Well, that did not go well. Specifically, example 914, I think it was. Yes. So example 914. We're having a bit of a thunderstorm here, so if you lose me, I guess I'll just have to finish it up and post it later. But anyways, I don't think it'll happen. My internet service provider is pretty stable with storms, so it shouldn't be a problem. The other thing I want to say, oh, in the email I sent out today, I was also reminding you guys that the video I made on Thursday, I had some problems with it. So I made more or less the same video again last night, and I posted that one instead and sent you all a link to that. So you can watch that if you haven't seen the previous parts of this chapter 9 up to center of mass. So now, example 914 says three people of roughly equal masses m on a lightweight air-filled banana boat sit along the x-axis at positions xa equals 1.0 meters, xb equals 5 point, excuse me, equals 5.0 meters and XC equals 6.0 meters measured from the left-hand end as shown in figure 924. Find the position of the center of mass. Ignore the boat's mass. If you're familiar with this banana boat, it's actually an inflatable thing, so it's perfectly normal to assume the boat's mass is pretty small. And what we're doing is finding the center of mass of the boat. So in principle, if you imagine this banana boat was actually rigid enough to hold up the people, which it's not, you could put your finger directly under the center of mass, again, assuming your finger is strong enough, or you could put a 2 by 4, for instance, thin edge up directly below the center of mass of the banana boat, and it would balance perfectly right there on that center with the center of mass directly over that 2 by 4 if the people were located like this. So that's part of the reason we're learning to calculate this. What we have is MA equals MB equals MC, and they're all equal to M, and XA is equal to 1.0 meters. XB is equal to 5.0 meters, and XC is equal to 6.0 meters. Oops, I wrote XC, I wrote X6 instead of XC. XC is equal to 6.0 meters. And we're asked to find the center of mass. So we want to know, and since they only gave us the X coordinate, they're really just looking for the X component of the center of mass, or the X coordinate, what we call the ordinate. It's called the ordinate and the abscissa. The ordinate and the abscissa. And if I remember correctly, the abscissa is technically the X one, and the ordinate is the Y one. So we want XCM, which equals, here's my solution. Oops. Solution. The formula we're using is XCM is equal to the summation from I equals 1 to N of M sub I X sub I over the summation from I equals 1 to N of M sub I. So that's what we're using here. And we'll go ahead and calculate it. So X center of mass is going to be, notice each term is going to have an M. So I'm just going to put the M out in front and then put parentheses. And what I'm going to have is 1.0 meters plus 5.0 meters plus 6.0 meters. And then all of that's going to be divided by M plus M plus M, which gives us, of course, M times 1 plus 5 is 6 plus 6 is 12. So this is 12.0 meters. That's a meter, not to be confused with the M. And the M plus M plus M is 3M. So you can see that these M's, not to be confused with the meters again, they actually cancel each other out. And now we're left with the center of mass being specifically 12 meters divided by 3, which is 4.0 meters. So that's actually what the center of mass of this banana boat is. Any questions on that? I will post some more videos. I haven't made your module yet, but there'll be a module there, and it's going to have a lot of videos of me solving center of mass problems, like using the calculus to calculate the center of mass of certain triangles and stuff like that. But also a pretty developed one where I take an actual framing square and determine the center of mass of a framing square. With that one, you can do it. You could do it with calculus, of course, but you can do it as if it's a discrete object by assuming that it's made up of either two rectangles or three rectangles, where you'd have a rectangle, and then you'd have another rectangle where the two rectangles meet. And of course, using the geometry of rectangles, you know that the center of rectangle is, halfway, half the width and half the height and half the thickness if you have a three-dimensional one. So you can just do it like that. But the big trick in that kind of problem is figuring out what's the mass of those parts, because you don't want to cut your, framing square up into three pieces just to determine the center of mass, because then it's no longer a framing square. So, anyways, just keep an eye out for those being in your module for this week. I should put that, if I don't get it up tonight, it'll be up first thing tomorrow. So that was example 914. Now I'm going to try example 915. So let's draw a line to separate this from the rest. And now we're going to say example 915. Example 915 says three particles in two dimensions. Three particles, each of mass 2.50 kilograms, are located at the corners of a right triangle whose sides are 2 meters. Excuse me. 2 meters and 1.5 meters long, as shown in figure 925. Locate the center of mass. So in this one, it's a little abstract because you've got three separate particles and they're not really connected to any part of each other or whatever. So what you could imagine is imagine that you actually made a really thin, light plexiglass triangle and then you embedded these tiny particles at the vertices of that triangle. Then, when you compute the center of mass, because the plexiglass would hopefully be much, much lighter than any of the individual masses, and that would cause the center of mass to not be quite so far off from what it is without the plexiglass there. And then you could balance those three on that plexiglass by putting your finger at the center of mass of that plexiglass. So that's a good way of thinking about it. Each of the masses M equals 2.5 kilograms. That's for each of them. And the diagram I'm going to use is like this. I'm going to take my y-axis and my x-axis. So there's my y-axis. I'm going to have a mass right here that's M sub A. All of them are the same though. So actually, maybe I'll say M sub I is equal to 2.5 because that means each of them, M1, M2, M3, are MA, MB, MC. Then I go over here 2 meters, which I'm going to say is roughly here. Oops, roughly here. And that one's going to be M sub B. And then up here, 1.5 meters is, yeah, that's 1.5 meters. There's going to be another mass, and this is M sub C, like that. Okay? And our job is to find the center of mass, and specifically we want the center of mass both in the X and the Y. So what we want is YCM equals question mark and XCM equals question mark. And there's really no reason for me to have written one before the other in that opposite order. I just did it because that was what came to my pen first. So what we're using is XCM is equal to the summation of M sub I, X sub I over the summation M sub I, and YCM is equal to the summation M sub I, Y sub I over the summation M sub I, like that. So let's start off with the X center of mass. So the X center of mass, just like we did before, we have a common mass of 2.5 kilograms. So I'm going to put that to the side and factor it out. So 2.5 kilograms. Of course, the denominator is going to have a 2.5 kilograms as well. But that's going to be 2.5 times 3 ultimately because it's going to be m plus m plus m. So I'll just go ahead and put a times 3 down here and that'll handle that. Now, the 2.5, the x-coordinate of mass A is 0. The x-coordinate of mass B is 2.0 meters. And the x-coordinate of mass C is also 2.0 meters. So that's what we had to do this calculation. You can see that the 2.5s are in fact going to cancel each other out, but 2 plus 2 gives me 4, and then 4 divided by 3 is 1.33. So our answer is going to be 1.33. That's one extra sig fig than we need. Meters is equal to XCM. So our X center of mass is 1.33 meters to the right. I'm using a scale where two squares is approximately 1 meter. So a third of a square would be actually two-thirds of a square would be one third. So I'm looking roughly right along this line is where the center of mass is in terms of X. So it's somewhere along this line roughly, because that's a whole meter over plus two thirds of a square, which is one third of a meter. So we've got that part. Now I'm going to calculate the same thing for the y center of mass. So y center of mass again, we're going to get 2.5 kilograms. And then we're going to have the y coordinate of m sub a is 0 meters. The y coordinate of m sub b is 0 meters. And the y coordinate of m sub c is 1.5 meters. And then all this would be divided by 2.5 kilograms times 3 again. Somebody's trying to come in, so let me click on that. Okay, so 0 plus 1.5 is obviously just 1.5, and then we're dividing 1.5 by 3, so that's going to give us 0.5. So our answer is 0.50 meters is equal to y center of mass. And that is it. So now we can try to look for specifically half a meter, and we see half a meter should be one square up. So in that case, the center of mass is right along here. And that means the two intersections, that's where we'd actually want to balance it. So if you went over 1.33 meters to the right of the y-axis and then went up zero point 0.5 meters above the x-axis, you'd be right in the center of mass for these three masses. And if you had them embedded in plexiglass of the same shape, then that would be exactly the point where you want to point your finger to hold it up as if you were a waiter or waitress carrying, three drinks on the edge of a triangular platter. Anybody have any questions on that? All right. Let's see if there's another one like this that I wanted to mention. Here it is. So I'm going to jump to example 917 real quick just to do that before we do an integral one. So let's jump to 917 and then I'll come back and do some integral ones, which I think is 916, which is a really simple one. But let's do that. So here is example 917. 917 says determine the center of mass of a uniform L-shaped construction brace shown in figure 929. So this is more or less like the framing square thing I was telling you about, except it's a little less advanced, but in other respects is just as advanced and maybe even a little bit more complicated. So I'm going to draw it, and then hopefully everybody will understand how we get started from there. So let me start off with a XY coordinate system. So there's my positive X axis. There's my positive Y axis. And I'm going to use the thickness of the square to be of this object to be one square. So let me draw one square, and it's supposed to be about 2.06 meters. So I'm going to say uh, I'm going to pretend like three squares is a meter just to make it a little bit easier to draw and make it big, of course. Now the other line is right here along the x-axis like that, but at that point it goes downward and then it goes downward for about 1.48 meters. And if we're assuming that three squares is 1 meter, so then it's going to go down to here for one, and then 0.43, or excuse me, 0.48 times 3 gives me 1.44. So I need to go another 1.44 down. So that's just a little bit less than a half. So I'm going to say roughly like that. And this distance is also the thickness of a square. So that means this object will be right about here. And now I'll draw these dimensions. I have it roughly the square. That's the main thing I was shooting for here. So what we're going to say is this is 2.06 meters to there. And to here, this distance is going to be 0.20 meters, which makes it out of whack with respect to the other stuff I was doing. But anyways, that's close enough. And this is going to be 1.48 meters, and that extends all the way down to here. And then this dimension to this dimension is 0.20 meters as well. Okay. Now, they didn't give us anything about mass, but we know that we can do this by basically realizing that this thing is made, it says cm of L-shaped flat object. So it's a flat object. It's probably very thin. And in fact, the area that we see is proportional to the mass. So, for instance, if you had 2.06 meters wide and you cut that in half, where it's still the same 0.20 meters tall, but now it's 1.03, you'd expect the mass to only be half as big as a 2.06. That's because you can see that the width times the height is directly proportional to the width times the height times the thickness, which would be the volume. And then, of course, volume, once you multiply that by density, which is the property of the material, you'll get the actual mass out. So that's all we're doing is we're just ignoring that third dimension and stuff like that. So what we can do to actually make this reasonable is I'm going to treat it as if it's two rectangles. I'm going to say, imagine this is two rectangles. One of them is going to be 2.06 meters by 0.20 meters by the thickness I'll just call T. Okay. Now, I'm going to assume that T is the same thickness for the other part as well. So you will see that the other part, number two, is going to be 1.4. Now, actually, I should probably put it in the same order that I did so we can see that something times something times something is three dimensions. I'm going to try to consistently say the first something before an x is the width, in other words, parallel to the x-axis. The second something is the height, in other words, parallel to the y-axis, and the third something is the thickness parallel to the z-axis, if you will. So in this case, I should call this 0.20 meters by 1.48 meters by thickness T. Okay. And really, what the mass of one is would be 2.06 meters times 0.20 meters times T times the density of the material. And see if you take the density of the material, which is kilograms per cubic meter, and multiply it by meters times meters times meters, that would give you the mass. But the key thing is you see that the mass is definitely proportional to the area. So that's what I'm trying to point out by writing this. This part's just the area. And then similarly, M2 would be 0.20 meters times 1.48 meters times t times rho. So again, we see that it is proportional to the area. And in fact, it has a common factor times the area. It's t times rho is the missing determinant. So we're good on that. We can treat that as the mass. And now I also have to find out what the center of mass is. Well, the center of mass for one is going to be this. So let's say XCM comma YCM for that first rectangle. Obviously, it's going to be halfway to the right, so that's 1.03 meters. And it's also going to be halfway upwards, so that one's going to be 0.10 meters. And then the x center of mass, or the center of mass for the second rectangle, x center of mass, y center of mass. In this case, it's going to be a half of zero point 0.2 over, but remember, zero point 0.2 starts at 2.06 minus zero point 0.2, so that's 1.86. So I'm adding zero point 0.1 to that 1.86, so that's going to be 1.96. That's how far the x coordinate of the center of mass of the vertical rectangle is over from the y-axis. It's 1.86 to the inside edge, and then we add another zero point 0.1 meter to account for half of the width of it. And then the other coordinate, of course, is down by half of 1.48, which would be 0.74. So 0.74. That's the center of mass of that one. So we can now use the center of mass formula for discrete objects to actually calculate the center of mass. So x center of mass is going to be, in this case, it's going to be m sub 1 x sub 1 plus m sub 2 x sub 2 over M1 plus M2. And I'm just going to write it with all these nasty details in there just so you'd see that it all going to cancel out and you don't have to do all this extra work. But here it is, M1. So the mass of 1 is going to specifically be 2.06 meters times 0.20 meters times t times rho times x1, which is 1.03 meters, plus now mass 2 is 0.20 meters times 1.48 meters times t times rho, and then the x of that is 1.96 meters, like that. And then all of that is divided by 2.06 meters times 0.20 meters plus 0.20 meters times 1.48 meters. And notice we had a common factor of t rho in there. So you can see that the common factor of t rho is going to cancel out with all these. And we can go ahead and compute the rest as follows. So I'm just like showing you all the gory details of what could actually take place, but hopefully you just multiply the two, the length and the width, and use that as the area, and you wouldn't even bother to put in a t or a row or anything like that. But I'm just showing you this is what happens when you try to skip that part. So on this first term, I get 2.06 times zero point 0.2 times 1.03, and that gives me 0.42438, and that's actually meters cubed. Plus, I'm going to do the same thing with the other one, so zero point 0.2 times 1.48 times 1.96 gives me 0.58016 meters cubed. And that's just how many digits my calculator's given me. Obviously, it's not the appropriate number of sig figs. We only had, in this case, two decimal places are 2 to 3 sig figs, depending on what we're doing. So with this, we had 3 sig figs times 2 sig figs times 3 sig figs. So really, these three should not be. And the same thing with this, these 3 digits should not be sig figs. And then in the bottom, we have 2.06 times zero point 0.2. That's 0.412 meters squared. And then zero point 0.2 times 1.48. That gives me 0.296 meters squared. And of course, we only had 2 sig figs there, so the third digit is not a sig fig. Now I can add up all this stuff. So I'm going to take the 0.42438 plus 0.58016, even though I don't need all those digits. That's going to give me 1.00454 cubic meters. And then I'm dividing all that by 0.412 plus 0.296. That gives me 0.708 square meters. And we really, when we added these two, we got up to two decimal places as sig figs. So the 4, the 5, and the 4 are not sig figs. And the same thing with this. That just means the 8's not a sig fig. So now I'm going to take the 1.00454 and divide it by 0.708. And that's going to give me 1.418. And notice that just gives me units of meters. And with this, I was dividing 3 sig figs by 2 sig figs. So really, I only have 2 sig figs. So the 1 and the 8 is not a sig fig. But that's our X center of mass, 1.4 meters roughly. Now we're going to go ahead and calculate the Y center of mass. With the Y center of mass, we're going to do the same thing. Obviously, the t and the rows are going to cancel out, but we're going to get the same thing, 2.06 meters times 0.20 meters times t times rho. Now we're going to take the x, or excuse me, the y center of mass for number one, and that's of course 0.10 meters. And then we're going to take that and say, oops, that was actually it. It's just 0.10 meters. And now we're going to take the other one, which is, as we learned before, 0.20 meters times 1.48 meters times t times rho. And then the y coordinate for the second guy is 0.74, like that. And then, of course, we still have the same stuff downstairs, which would be 0.412 meters squared plus 0.296 meters squared. And now we can go ahead and calculate this. So again, oh, all this was times TP, so I should put that T row like that, and we can go ahead and see that this T row cancels out with that T row and that T row. And in this case, we're going to get 2.06 times 0.2 times 0.1 gives me 0. Oops. Gives me 0. Dang it, why is it? There we go. 0.0412, and that's meters cubed, and we only had 2 sig figs, and that was all multiplication, so that means this 2 is not a sig fig. And then we're saying plus 0.2 times 1.48 times 0.74, and that gives us 0.219 9.04. In that case, we only had two sig figs as well, so the 9, 0, and 4 is not a sig fig. And then the denominator we know is 0.708 square meters, but that was really 0.41 to two decimal places was significant, and 0.29 to two decimal places was significant, so I can underline that. Now I'm just going to add these top quantities, 0.041 plus 0.21904 equals 0.26024. Now, in this case, we actually had two decimal places, but we didn't clear the getting higher than a whole number, so we don't have three sig figs as a result of that. We still only have two. That is in meters cubed, and then divided by 0.708 in meters squared. So I'm going to take this 0.26024 and I'm going to divide it by 0.708, and that's going to give me 0.368, and that's just meters. And of course, I divided two sig figs by two sig figs, so the 8's not a sig fig. And this tells me that the center of mass of this thing, XCM, and notice sometimes I do write the X and Y as capitals when I'm talking about center of mass, and I often put them as an ordered pair because they really are technically a point. And if we were doing it in three dimensions, it'd be technically ordered triple instead of an ordered pair. But in this case, we're going to call this roughly 1.4 meters, comma 0.37 meters is the center of mass of this sort of framing square looking structural member, something along those lines. I wonder what happened here. Oh my goodness. That that 0.74 was technically supposed to be a negative. So let me correct that real quick. Notice I'll write this in blue. That's the only color we're not using. I thought I even, nope, I just left the negative off in here. I'll write it right here so we'll know. So there's the negative there. Supposed to be negative. So the difference would be instead of having this plus 2.21904, we're going to say, no, this is minus, and now I'm going to say 0.0412 minus 0.21904 gives me a different answer. So I'm going to say right here, this answer is now going to be negative 0.17784. Still only good to two sig figs though. So now I'm going to take 0.207, or excuse me, 0.17784, and I'm going to divide that by 0.708, and that's going to give me negative 0.251 meter. So instead of the answer that I wrote here in the Y, sorry about this, everybody. Instead of the answer that I wrote here in the Y, I'm just going to call it negative 0.25 meters. There you go. So I apologize for making that boo-boo. I should have said it. I should have known it. I mean, I had it right there, and I just didn't write down the negative in front of the 0.74. So anybody have any questions on that? All right. So now we're going to go back and do something like example 916. And we're going to do a little bit more than that as well. But example 916 is find the center of mass of a thin rod. So here we go. Example 916. What they give us is show that the center of mass of a uniform thin rod of length L and mass M is at its center. Okay, so we're supposed to just show that it's at the center. And what we're given is the mass of the rod is m, and the mass per unit length is lambda. That's what we're given. Okay. And A, show CM at center. And then B, they want us to determine the center of mass of the rod, assuming its linear mass density, lambda, its mass per unit length, varies linearly from lambda equals 0 to lambda equal 2 lambda 0 at the right end. So if lambda is equal to lambda 0 at x equals 0 and 2 lambda 0 at x equals L. Oops, they didn't give us a lambda. Sorry about that. They gave us L. I don't know why I wrote that as a lambda there. I saw the lambda somewhere. Oh, that's what it was. I saw it in the actual answer below. So that's the actual length. And this is at x is equal to L and linear. Okay, so that means the lambda of x is a linear function, and in this case, we want to calculate the center of mass for this. So that's the two questions here. We're going to start off with solution. X center of mass is equal to the integral of x dm over the integral of dm, where dm is equal to lambda DL. That's what we're going to use since this is obviously a one-dimensional shape object. Now I want to show you how we go about doing this so you'll have some sense of how to do it. And this is probably somewhat like some of the calculations you might have had in Calc 1 or early Calc 2 when you first started going over integrals. That's one of the things they do is show you how to calculate centers of mass and stuff like that. What we're picturing here is a rod who's really, really thin perpendicular to the x-axis, but long parallel to the x-axis. So what we mean by that is this length right here is L and its mass is big M. And in order to use our formula, we're going to start off with part A. In order to use our formula, I'm going to imagine a little bit of width along this. I'm going to call this little chunk dm, and its width, notice, is parallel to the x-axis, so it seems reasonable that that should be a differential change in x. And in fact, you would probably say that the left edge of this blue mark is at x and the right edge is at x plus dx. So we're going to say that distance is dx, and dm therefore is lambda dx. So that's how we use the lambda dl. The dl happens to be parallel to the x-axis. So why would we use dl? Would you use dx? And in the part A, lambda is a constant. That's what it means when it says something is a uniform rod. It means the lambda or the sigma or the rho that I showed you is a constant. Okay. So now we can go ahead and say uh, top. So remember the formula for a center of mass has a top and a bottom. So I'm going to do the top first, which is the integral of x dm. Now, the other thing we have to realize, and I already said this sorta, but the distance from the coordinate origin to the actual dm is the distance x. So that's what we actually need. We need in the integral, the x is the distance from the coordinate origin of that particular axis up to the dm. So in this case, we're going to say we have the integral of x dm is equal to the integral of, we're just going to say x times lambda dx. And of course, lambda is a constant. In fact, if you want to know what lambda is technically just m over L. So note, in A, lambda equals m over L. So that's all we're using there. And we can immediately see that this becomes equal to lambda times the integral of x dx. And that goes from x equals 0 to L. So we're going to get, in fact, 1 half lambda L squared for the top. Now the bottom. The bottom is the integral of dm, and it literally means the exact same dm we had before. So I'm going to integrate from 0 to L of lambda dx, which equals lambda times the integral of dx from 0 to L, which is obviously equal to lambda times L. So x, center of mass, is equal to the top divided by the bottom. And that's just an easy way for me to keep this where I don't have to do two integrals at once and do all that crazy stuff. So I just wanted to restate at the end. I'm just going to divide the top by the bottom, and I have 1 half lambda L squared for the top, and I have lambda L for the bottom. You can see that at least the exponent of 2 disappears with the L downstairs and leaves an exponent of 1, and the x can't, or the lambda cancels out with the lambda. So I didn't even need the lambda, but specifically what we just discovered was that the xcm is in fact equal to 1 half L, which is what we were asked to show. So I'll say QED, quoad errata, quoad demonstratum, at, I can't remember what the E was, but oh well. So that's it for part A. Anybody have any questions on that? Open up this chat window in case anybody's typing anything. I don't see anybody typing anything. That's good. Now, what we want is for part B, we want lambda to be a linear function. So what we can do is we can say lambda of x is going to equal, remember it's supposed to be lambda at x equals 0, so that's going to be 2x plus lambda 0, and this is going to be 2x over L, I think. So at x equals 0, we're just going to get lambda 0, but at x equal L, we'll get just 2 plus lambda 0, so that's not right. So let's think of another way. We do know it's linear, so in principle, we can go back to our very beginnings and say that lambda of x is equal to some mx plus b. Now, this is really just assuming the worst. I can think of a formula right now to come up with it, but just in case you're not quick and savvy to come up with that, sometimes it's best to show you exactly how I do it in the worst case scenario where my brain's just stopped working. So I know linear has the form y equals mx plus b. So I'm replacing the y with lambda of x, and I'm replacing the function with mx plus b. And what I know is when x is equal to 0, then lambda of x is supposed to be lambda 0. So I can plug this in. I'm going to say lambda 0 is equal to m times 0 plus b. And that tells me that b has to equal lambda 0. Now I also have this other piece of information that says when x is equal to L, then lambda of x is equal to 2 lambda 0. So in this case, what I'm going to do is say 2 lambda 0 is equal to m times L plus, we already figured out that b was lambda 0, so I can put that there. And that's going to allow me to figure out what L is. I can subtract lambda 0 from each side, and I get lambda 0 is equal to m times L, and that means m is equal to lambda 0 over L. So our lambda of x is supposed to equal specifically lambda 0 over L times x plus lambda 0, which you could also write as lambda 0 times x over L plus 1. So that's a way of doing it. And that's just assuming the worst, that you couldn't work it out or whatever. If they said it was quadratic, you'd say instead of mx plus b, you'd say a1x or a2x squared plus a1x plus a0. And then you solve for the three a1, a2, and a0. So anyways, now that I have that, I can go ahead and work on the top. The integral of x dm is equal to, using the same diagram that we had before, it's going to be x, but now the dm is again lambda dx, but the lambda is a function, so it's going to be lambda 0 times x over L plus 1 times dx. And of course, that lambda 0 can just come out in front, and I'll get lambda 0 out here, and I'm integrating from x equals 0 to L of, now I'm going to distribute the x. It's going to be 1 over L times x squared plus just plain x dx. So we see where the little L came in. We're all good with that. The integral of 1 over L x squared would be the 1 over lambda, or excuse me, the lambda 0 is still out there. So I don't know why I wrote 1 over there. Oh, I do. I just was thinking of the next step. I'm going to actually do the next step on the next line. So I'm going to say lambda 0 times, in this case, I'm going to say x cubed over 3L. And then, of course, the integral of x would be 1 half x squared. And now I'm going to evaluate that at 0 and L. And that's going to give me lambda 0 times L cubed over 3L plus 1 half L squared, and then the minus 0 part is just going to be 0. So we can simplify this a little bit better. We can say it's lambda 0, and then you notice that this is going to be 1/3 L squared plus 1 half L squared, and 1/3 plus 1 half. If you multiply the 1/3 by 2 over 2, you get 2/6. And if you multiply the 1 half by 3 over 3, you get 3 over 6. So 2 over 6 plus 3 over 6 is 5 over 6. So we're going to get 5/6 L squared. Hopefully that all worked out. All right, now we're going to do the bottom. And the bottom is just the integral of dm, which is lambda 0 times the integral of x over L plus 1 times dx, and that's integral from x equals 0 to L. And in this case, we're going to get lambda 0 times x squared over 2L plus x from 0 to L, which gives me lambda 0 times L squared over 2L plus L, just like that. And of course, L squared over 2L just becomes 1 half L. 1 half L plus L is 3 halves L, so it's going to be 3 halves lambda 0 times L. So finally, YCM is equal to top over bottom gives me lambda 0 times 5/6 L squared divided by 3 halves lambda 0 times L. You can see that the exponent on the L cancels out, leaving a exponent of 1. You can see that the lambda zeros cancel out, and we end up getting 2/3 times 5/6 times L. And the 2, of course, can cancel out, leaving a 3 in the bottom. So we're going to end up getting 5/9 L, assuming I didn't make any careless mistakes. So the center of mass in this case is 5/9 L. Let's see if they got the same thing that I did. Yes, they got 5/9 L, and that's it. We say, and I don't know why I said that was YCM. That was clearly an XCM. So XCM is equal to 5/9 L. Anybody have any questions on that one? All right, let me show you one more shape. One thing we can do, yeah, I think that's good. One thing we can do is we can find the center of mass, for instance, of a rectangle, or let's say of a triangle. So I'm going to do that. Let's see, does your book actually do a triangle? I can't remember if it did or not. There's that, there's that. It didn't do that. It did not do that there. Let's see on the next page. No, okay, so let me go ahead and show you how to calculate the center of mass of a triangle. Now, if you take the calculus-based statics course, you will need to be able to calculate this kind of stuff, the center of mass of a weight distribution, of a force distribution, or something like that. That's called the centroid of force. So it's the exact same calculation that we're doing here, except we're doing center of mass here, whereas you're doing a center of force or a centroid of force, something like that. So it's very valuable. So either way, you need to know the rule, and the rule is basically this: if you have a uniform triangle, then the center of mass is going to be about 1/3 of the way from the thickest part to the thinnest part in each direction. And you'll see how that works out in a second. So let's start off with, let's just call this Mr. Y's example. Okay. So what I'm going to do is I'm going to draw a coordinate system. Here's my x-axis. There's my y-axis. And in your calculus class, they would call this a homogeneous lamina. Okay. Homogeneous basically just means that every part of it is exactly like every other part. It's uniform. And in fact, if you cut any individual part to 1 nanometer by 1 nanometer by 1 nanometer and you weighed that, you would get a certain mass. But if you grabbed another part from any other place on the object and cut out a 1 nanometer by 1 nanometer by 1 nanometer chunk, it would weigh the exact same thing. That's homogeneous. The fact that it's a lamina means that it's two-dimensional. So we're pretending like it's a two-dimensional object instead of a three-dimensional object. And, like I said, a street sign's a good example of that. Sometimes street signs might be 4 or 5 meters wide, 2 or 3 meters tall, and literally on the order of a millimeter thick. So that's literally 1/1000th, or even, 1/10,000th the size. But what I'm going to do in this case, I'm going to assume this is uh, I'll say it this way: calculate the CM of this triangular homogeneous lamina, i.e., a uniform triangular plate. So in physics language, we would just call that a uniform triangular plate. In the math world, they would call that a homogeneous lamina. Okay, so now I'm going to go ahead and draw what I mean by that. I'm going to say the height of this triangle is h, and I'm going to say the width of this triangle is w, and in fact, it's going to go from here to here, and that is going to be my actual triangle. Okay, solution. XCM is equal to the integral of xdm over the integral of dm. YCM is equal to the integral of ydm over the integral of dm. One of the main things you got to remember when you're doing complex integrals like this is whatever your integrand is, you cannot have the value of that integrand, which in this case would be like x in the top of the x center of mass or y in the top of the y center of mass. You can't have that x value vary a macroscopic amount over the size of the dm. So when I go to choose an XDM, when I go to choose my DM, I need to make sure that the X on one side of it is not macroscopically different from the X on the other side of it. So to do that, what I'm going to do is imagine a little rectangular Riemann sum type rectangular thing like this, whose width is actually dx. So that way the left-hand side has a x coordinate of x and the right-hand side has a x coordinate of x plus dx, so that they only differ by an amount dx, which is infinitesimally small, so that's fine. Now, the equation, of course, for this will be helpful, so I'm going to go ahead and show you that as well. This equation, because what we're going to do is we're got to figure out the mass, the dm, if you will, of that little rectangle I just drew. And the height of it, of course, is the functional value. The y as a function of x is a line that represents the hypotenuse of that triangle. If I subtract from that 0, that'll give me the height of that rectangle. So I need to know what the equation for that rectangle's hypotenuse is, and that equation is y equals mx plus b, and we can see that the slope is rise over run, so that's going to be h over w for the slope, and then times x. And then you can see that the origin is where it hits the y-axis. So that's the whole function. It's y equals mx plus b, but the b is 0 in this case. So I can now say that this red differential mass element it's basically a rectangle, and its height is h over w, times x times dx. And I should say the mass of this is going to be, let's see, calculate the center mass of this triangular homogeneous mass, homogeneous lamina, if its mass is big M. So I'm just going to call its mass big M and just go with that, okay? Because of that, since it's uniform, we can go ahead and figure out, I'll say note, we said dm is equal to sigma dA, which also implies that sigma is dm over dA, which in this case is just going to be m over 1 half h times w. So that's actually what the sigma is. And we don't necessarily use that all the time, but I always want to show it to you when we first start off so you can get the hang of understanding what the sigma is, what the lambda is, what the rho is. So since this is uniform, all I had to do is take the total mass and divide it by the total area. And in this case, it becomes lambda is equal to 2m over hw. And we may or may not use it. It's not a big deal. All right. So now I can say uh, xcm, and I'm going to say top. So the top is the integral of x dm. The integral of x dm is going to be the integral from x equals 0 to, in fact, w of x, which is the distance, by the way, from here to here is x. That's the x that we want. So I'm going to write x right here. And then dm is just going to be sigma. And that's what I left off in this. Let me do this real quick. There you go. I left out the important factor. dm is equal to sigma times dA. And that's the dA, the h over w times x dx. That's the dA. So just in case anybody missed that, this is dA. And I need to extend that purple to make sure everybody knows that the dA extends all the way to there. And this purple stops right there. Okay. All right. So now I'm going to go ahead and write times sigma times h over w times x times dx. So we've got a lot of stuff that can fall out in front. The constants specifically are sigma h over m. So I'm going to write sigma h, or excuse me, sigma h over w, not m. That happens to me a lot. So keep an eye out for me changing that w to an m for some reason. All right, now I've got the integral from 0 to w of, all I have left is x squared dx. And of course, the integral of x squared is 1 half x squared. So we're going to get sigma h over w times 1 half w squared, because when we evaluate it at 0, you get 0. So now we can see that the top is going to be sigma hw over 2, because the w and the w squared in the top canceled out the w in the bottom, so I just have sigma hw over 2. Any questions on that? Okay. I feel like something might have be amiss. Oh, wait a second. It's x cubed over 3. My fault. Everybody's catch my goofy integral? The integral of x squared is not 1 half x squared. The integral of x squared is 1/3 x cubed. Sorry about that. Glad I caught it then. So this is going to be times 1/3 w cubed. Now that makes a little bit more sense. The units weren't working out. That's what made me think it was wrong. I had sigma hw over 2. Well, sigma has units of mass per unit area. So if I multiplied that by the hw, that would just be units of mass. I shouldn't have units of mass for the integral of x dm. So I knew something was wrong, and sure enough, I realized that I'd forgotten to properly integrate it. Now I have the w cubed canceling out with the w downstairs to give me w squared. So now it's going to be sigma h w squared over 3 is the top. Now I can do the bottom. Anybody have any questions about that top before I go on to the bottom? All right, so I'm copying the same thing over. It's without the first x. It's sigma h over w x dx. So that's going to be, and that's integrated from 0 to w, and that's going to be sigma h over w times the integral x dx from 0 to w, and the integral of x is 1 half x squared. So this time I really get the 1 half x squared. It's going to be sigma h over w times 1 half w squared. Now you can see that that's going to be sigma h w over 2. Now the x center of mass is the top divided by the bottom, and our top was sigma h w squared over 3 divided by sigma h w over 2. You can automatically see that the sigma h is going to cancel out with the sigma h, and one of the w's is going to cancel out with the w up there. But you can also see that the 2 is going to come on top and the 3 is going to come on the bottom, and all we have left is 2/3 w. Notice that that is 1/3 of the way from the thick part. The thick part is at the W end of the X side of the triangle. So the triangle goes from a point at x equals 0 all the way to a height h at x equals w. So that's the thick part over here. If I go 1/3 of the way from the thick part to the thin part, then that gives me exactly 2/3 w. So that's what I was meaning by the general formula for a uniform triangle is always 1/3 of the way from the fat part to the thin part. Any questions on that one? The Y center of mass is a little more complicated. Let me draw a diagram again just so we can get that started. I'll draw the diagram a little smaller this time. And I'm going to call this distance W, and I'm going to call this height H, and this is going to be our triangle right here to here to there. Now this time I got to be careful specifically because my formula is YCM is equal to the integral of YDM over the integral of DM. So I need to make sure the Y doesn't change significantly from one side of the DM to the other side. So what I'm going to use for my DM is, you can imagine a actual rectangle like this, but specifically I only want this portion of the rectangle. Well, this portion is x equals w, and this equation right here, this equation can be written as x is equal to w over h times y. So the other side would be basically that function x. So I want to say w minus w over h times y is the part of that rectangle. And specifically, we also know that the thickness of that rectangle is dy, and that means this little part is going to be dm, which equals sigma dA, and that's going to be sigma times W minus uh, W over H times Y times dy. So that's really what's going to happen here. Now I can compute the top and the bottom, so on and so forth. So YCM top integral YDM is equal to the integral from y equals 0 to h in this case of, I'm going to go ahead and write the y down, and now I got to write the dm, and the dm is sigma times w minus w over h times y times dy. like that. And in fact, you can see there's a common factor of W that I can pull out, and I'm going to do that. So I'm going to say it's sigma W integral of 0 to H of uh, y minus y squared over H dy. So we can go ahead and continue with this. I'm going to say sigma W integral from 0 to H of specifically uh, when I distributed that y, I got y times 1 minus w over h times y. So that's y squared. That gives me the y squared over h. Okay, so that works out fine. I don't need an integral at this stage. I need to go ahead and compute the integral. So the integral is the sigma times the w still there. The integral of y becomes 1 half y squared. So that's going to be 1 half h squared. And then the integral of y squared is going to become 1/3. So that's going to be negative uh, h cubed over 3h. Oops, that's supposed to be a 3. Over 3h, like that. And of course, the 0 side of the integral gives you 0. But now what you see is you have a common factor of h squared. So I can say sigma w h squared times 1 half minus, in this case, it's 1/3. So 1 half is going to be 3/6 and 1/3 is going to be 2/6. So 3/6 minus 2/6 is 1/6. So we're going to get 1/6 sigma h squared w is the top. Anybody find any errors in that? Now I've got to work bottom. So the bottom is the integral of dm, which is just the integral from 0 to h of just the mass part that I had before. So that was sigma w minus w over h y dy. That's going to become sigma w times the integral of 1 minus 1 over h y dy from 0 to h, which is going to give me sigma w times the integral of 1 just becomes y, evaluated at h is h, evaluated at 0 is 0, minus the integral of y times 1 over h would be 1 over 2h h squared when evaluated at h, and of course be 0 otherwise. So now we have 1 minus 1 half, and that's going to give me sigma w common factor of h, and then 1 minus 1 half is going to be just 1 half. So I'll write it this way. Sigma hw. So ycm is equal to top over bottom. And the top we found was 2/3, or excuse me, was 1/6 sigma h squared w. And the bottom we found was 1 half sigma hw. So we can see that the w's cancel out this time, w and w. The sigmas cancel out this time, and of course, one of the exponents on the h does. So now the 1 half is going to become a 2 in the top, and the 1/6 is going to become a 6 in the bottom. So 2/6 is 1/3, and we're going to in fact get 1/3 h, which again is 1/3 of the way from the wide, from the thick part of the triangle, which is the bottom, up to the narrow part of the triangle, which is y equal h. So in this case, we've got the y center of mass is 1/3 h. Any questions on that? All right, so that's sort of some of the toughest types of integral stuff that you could possibly do. If you want to get some practice, I would say try these exact same ones, but maybe try with sigma being proportional to, say, x, and just find the x center of mass instead of the x center of mass and y center of mass. So you could do that. And you could also do the y one, and in that case, you'd say sigma is some constant times y, or some constant times y squared, or some constant times y cubed, or something like that, and just calculate the y center of mass, and that would give you it as well. It would be a little bit more complicated if you tried to do that where you're getting both the x and y center of mass when you're letting the variable, the sigma depend only on the variable x or only on the variable y. That's why I'm saying if you're going to make the sigma into a function of y, only do the y variable or the y center of mass. If you're going to make the sigma only a function of x, then only do the x center of mass for that one. Okay. And by that, you can still use the 1/3 rule for the other one, for the one that you don't do. Any questions on that, anyone? It's perfectly normal if this feels like you just got blown away from some scary high level math or something like that. So, don't freak out if that's the case. Now, we're up to section 9.9, and that's called the center of mass and translational motion. What your textbook author is doing here is he is trying to rewrite basically what is Newton's second law, but in terms of a bunch of masses added up. So we're imagining the system not being a single mass m, we're imagining a system being a big mass M that is in fact equal to a summation from I equals 1 to M, to N of M sub I. So if you had a big M is the total mass, and it was broken up into N little masses, M sub 1, M sub 2, M sub 3, on up to M sub N, then we're trying to imagine that and apply Newton's second law. And that's what your author is doing. Let me show you specifically. So this is section, subsection 9.9, and it's called center of mass and translational motion. So that's what we're looking at. So, what your author is doing is he's imagining where would be, for instance, the center of mass of this big object. So, if the object had a mass m, and that big M is M1 plus M2 plus dot 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 plus M sub N, which equals the summation from I equals 1 to N of M sub I. If that's the case, then M times RCM is equal to the summation from I equals 1 to N of M sub I R sub I. In other words, you can treat it as a big mass M and say its center of mass is pointed to by the vector R sub CM, like I have written on the right. But in order to do that, you've got to use the sum of the masses to figure it out. So you've got the sum of the masses M sub I, R sub I. Now, if you take the derivative of this equation, then you say, let's say d by dt of both sides, then what you get is specifically m, which is a constant, times drcm over dt is equal to the summation over I of m sub I dr sub I over dt. And what that tells you is that we've got m times the velocity of the center of mass is equal to the summation over I of m sub I v sub I, which you can recognize as the actual momentum that we talked about. Remember, momentum is mass times velocity, but now I have the sum of all the individual masses, so it's the total mass times velocity. And if we took a second derivative, if we now said, okay, let's take d by dt of both sides like this, then what we're going to get is m times dvcm over dt is equal to the summation over I of m sub I a sub I. So, in fact, what we found is basically Newton's second law again. Newton's second law says the mass times the acceleration is equal to, in this case, the summation of the masses times each acceleration in each case, so on and so forth. So, we can make the argument that m times a center of mass is equal to F1 plus F2 plus dot 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 plus Fn like that, and that's just equal to the summation over I of F sub I. In other words, that's the whole right hand side is M sub I, A sub I, so each of those is F sub I. And then M1 times A1 is F sub 1, M2 times A2 is F sub 2. That's why we got all that. So what we ultimately can figure out is that M times A, center of mass, is just equal to the summation of the forces that are acting externally on the system for a constant M. If it wasn't a constant m, then we'd use sort of the same equation that Newton's second law had when we did it earlier, specifically F equals dp dt. But the main thing that we're figuring out here now is that we can treat the object as if it's a point particle when we're dealing with its center of mass, but the individual parts we can work on as well. We don't really have all the tools yet. We still have to figure out torque and all this stuff and moment of inertia. That's going to come in the next chapter and the chapter after that. So we first got to do all that. But I just wanted to show you a little bit about what he's talking about. In a conceptual example 918, he says a two-stage rocket. A rocket is shot into the air as shown in figure 932. At the moment the rocket reaches its highest point, a horizontal distance d from its starting point, a prearranged explosion separates it into two equal parts. Part one is stopped in midair by the explosion and falls vertically down to Earth. Where does part two land? So what you have to realize is that's the conservation of momentum problem. The object was taking off and was flying horizontally, and then when it got a distance d away, it exploded in such a way that one half went straight down. In other words, losing all the x component of momentum. That means the other half is going to take in all that x component of momentum that one originally had. That's all going to go to that other mass. So that other mass is going to land probably somewhere like twice as far away instead of a distance d away that we would have expected. So that's what they're talking about in conceptual example 918. Now, ultimately, that was just a conceptual example. Ultimately, we can also say that dp over dt. Notice I used a capital P here because in this case, I'm not talking about a P of a single particle, mass 1 times velocity 1. I'm talking P as the mass of a system of mass, or the momentum of a system of masses, like the flock of birds we talked about. So this would be m1v1 plus m2v2 plus m3v3. That's what that capital P represents. And that could, in principle, equal m times d center of mass over dt. But it's definitely, if that's the case, then you could just call that a center of mass. Or we could go ahead and say dp dt, again capital, is equal to the summation of the external forces acting on the mass. In other words, we leave off all the M1 acting on M2 and M1 acting on M3 and M1 acting on M4 and so on and so forth, as well as M2 acting on M1 and M3 acting on M1 and M4 acting on M1. All of those are just internal forces. We don't put them in at all. All we do is only the forces from anything that's not part of the system. So if your system was a flock of birds, any forces that one bird put on the other is not one that you put on the right hand side, in this case of Newton's second law. But if another airplane or a drone flies in and hits the birds, then yeah, that's an external force. Okay. And that's the trick in a nutshell. Basically, we can treat F equals ma and treat any object as if it's a point particle. But what we're doing in that case is we're treating it as we're actually just treating the center of mass of the system. And then later we'll learn, hey, if the object was actually rotating before all that, then we can use our understanding of rotational motion to figure out how much it'll rotate it in 1 second, 2 seconds, 3 seconds, or just before it hits the ground, and so on and so forth. So that's all we have to do next is put all that together. We're now finished with chapter 9 completely. I don't really have much time to go into chapter 10, so I don't think it's very good for me to take time to do that. We got 30 minutes because it's supposed to go to 7:40. Yeah, I guess I can fit some of that in. Let me go ahead and jump into chapter 10 just a little bit, and I'll give you some of the simple stuff so it won't be so bad. But we'll jump right into that. So, chapter 10 is called Rotational Motion. Chapter 10, Rotational Motion. So, chapter 10, rotational motion. And the subsections are angular quantities. So, we're going to have a set of variables, just like we had a set of variables in kinematics. We had the variable x and we had the variable d. X and d, x was a coordinate and d was a distance, or you could have said d was a displacement. That was another variable. We also had v, but we also had s, where v was a velocity and s was a speed. We had time, t. We had a acceleration, v velocity, so on and so forth. Well, we're going to have variables like that too that are rotational, and they're going to be rotational analogs. Specifically, for instance, we have the equation. If we start out from the very beginning, we learn that speed is distance divided by time, meaning you just divide the distance traveled by the time taken, and that would give us our that would give us our average speed. But then we learn that the average velocity was delta x over delta t. Remember, that's a change in displacement. Specifically, it's a vector that points to the final point minus a vector that points to the initial point. You subtract those two and then divide it by the time taken, and that gives you a vector quantity that is the average velocity. And we could say, in fact, that the instantaneous velocity was dx over dt, at least in that one-dimensional motion. But in three-dimensional, we call it dr dt like we did just then. When we integrated this, or actually when we integrated another one, we were able to get an acceleration. But I'll first start off with acceleration on average is delta v over delta t. So that's the average. And the instantaneous acceleration A is dv dt. And from this, we were able to come up with the conclusion that v is equal to v0 plus at. And that's for a constant acceleration, but it also happens to be the exact same equation as the a average equation. And then when we integrated that again, we got x is equal to 1 half a t squared plus v0t plus x0. And then if we solved the v equals v0 plus at for t and plugged it into this x equation, we also got v squared equals v0 squared plus 2a x minus x0. And there was this other one that we used, in fact, today, or last night I used it, and it's very rarely used, but these last four are only true when the acceleration is a constant, and that is that v average could be v0 plus v1 over 2, but this is for a equals a constant. Okay, so you see sort of all the kinematic equations and all the special variables that we learned about in the first chapter. Now watch this. It turns out there's going to be an exact analog in rotational motion. Specifically, omega bar is going to be delta theta over delta t. And omega is going to be d theta over dt. Now, there is a way to construct these vectorially, and we'll talk about that later, but it's sort of a pseudo vector thing, so it doesn't really work out quite so nice. So that's why I'm not writing them as vector quantities. There's also a rotational analog to the acceleration, and that quantity is called alpha, and the average alpha is delta omega over delta t, whereas the instantaneous alpha is d omega over dt. And then, of course, guess what? We've got exactly the same equation. We've got omega equals omega 0 plus alpha t. We've got theta equals 1 half alpha t squared plus omega 0 t plus theta 0. We've got omega squared equals omega 0 squared plus 2 alpha theta minus theta 0. And we don't really have, I guess we could have one, but I've never used it. So I'm not going to say that because I've never used it and I've never even tried it. But there might actually be an equivalent. Omega bar is equal to omega 0 plus omega 1 over 2. I suspect that should be right, but having not checked it recently or ever maybe, I decided not to do that. So all of this hinges on your understanding of one thing, and then it sort of all falls out. If you imagine a circle from trig, okay, you know, for instance, that the circle, you can take its radius r and then let it sweep out an angle theta. And then this little arc length, which is literally a bent distance, this little arc length s is given by r times theta. Y'all remember that as the definition of radians? S equals r times theta. That clearly gives you, in the event that you want to find the circumference, the whole distance around, we know that's 2 pi r. So you'd write on the left-hand side, in place of s, you'd write 2 times pi times r, big R. And then on the right, you'd write r times theta, and that would tell you, oh, evidently when I make a complete rotation, that must be 2 pi radians. And that's how you come up with this. But if you take the derivative of s with respect to time and do the same thing on the other side with r times theta, assuming r is a constant, you get ds dt, which is in fact a velocity, and that's equal to r times d theta dt, which we learned earlier, d theta dt is omega. So we've got v is equal to r times omega. So that's a very, very important equation that relates the velocity, what we call the translational velocity, to the angular velocity omega. That's what omega is called. It's called the angular frequency or the angular velocity. And we just found a relationship between it, between the regular velocity, the translational or tangential velocity, to the angular velocity omega. Now, if I take the derivative of that, d by dt of v, and I take the derivative of the right hand side as well, d by dt of r omega, again, assuming the r is a constant, then I get dv dt is a, r times d omega dt is alpha. So in fact, we have another equation, and now it looks like if I went ahead and replaced alpha with a over r in the purple equations and omega with v over r in the purple equations, I would get exactly the same equations I had in the blue equations. So that's like one way of me verifying that all these equations that I just wrote down in purple are exactly analogous to the ones in blue, and you can sort of see how they come about by using these expressions. All these expressions, the purple ones that I wrote down and the ones that I put in the red box, are all going to be used, so you need that. Now, we do have a rotational analog to mass, and in fact, we'll have m equals mass. In this case, it's going to become I equals moment of inertia. That's what we call it in physics. And you might know of it a little differently in engineering, but it's a summation from I equals 1 to n of m sub I r sub I squared. R I is equal to the integral of r squared dm. That was that integral formula I was hinting to earlier that you're going to do next. So that's what our mass is. We also have a rotational analog to momentum. We have P is equal to m times v. Well, actually, I should probably put that a little lower. Let me go ahead and, because I wrote the I under there, we're also going to have P equals m times v. And just as you'd expect, well, you didn't necessarily know the letter that we're going to represent rotational angular momentum, or what we call angular momentum, was going to be L, but the rotational analog to mass is supposed to be the moment of inertia, and the rotational analog to velocity is supposed to be the angular velocity. So L is actually going to turn out to be I times omega, and I put a vector symbol over it for a good reason. Okay. Now it also happens that L can equal R cross P as well, where P is equal to MV. So that's another thing we can do as well. But we can also see kinetic energy. K equals 1 half mv squared. Well, guess what? There's a kinetic energy rotational as well, and that's going to be 1 half I omega squared. So you can see we have a rotational analog to essentially everything. And a lot of times it has the same units, other times it doesn't. You can see, for instance, angular momentum has a different unit than momentum, and mass has a different unit than moment of inertia. In the physics world, moment of inertia has units of kilograms meter squared, and mass just has units of meters, or excuse me, of kilograms. Momentum has kilograms meters per second, but in angular motion, angular momentum has meters times kilograms meters per second. So it's kilograms meter squared per second. But kinetic energy both in rotational and translational both have units of joules. So the big thing we have to start off with is S equals R times theta, and then the derivative of that gives us V equals R omega, and then the derivative of that gives us A equals R times alpha, and then you can sort of make sense of the blue equations turning into the purple equations, only I would say that these ones down here, these should have been written in purple, but I was just flying by the seat of my pants and didn't do it. So, any questions on that? So section 10.1 was angular quantities. I more or less covered all of that in more details than was really meant to be in that first section. Then section 10.2 does the vector nature of angular quantities. That's where it shows you that some of these vectors that we're going to pretend like are vectors, like the omega one, is what we call a pseudo vector. And they have a very distinct property that makes them clear that they're not a vector. When you look at a vector in a mirror, you should get the same sort of results when you're looking in the mirror image as you do in the regular image, but with these pseudo vectors, you do not get that. So that's what they're talking about there. Section 10.3 is on constant angular acceleration. As you can imagine, we could start off with the exact same scenario we did in chapter 2 when we did kinematics. we started off with A equals a constant and realized that A is equal to dv dt, and we integrated that and we ended up getting V equals V0 plus AT. Well, guess what? If you assume alpha is equal to a constant and you say that alpha is equal to d omega dt, you can integrate that and you'll end up getting omega equals omega 0 plus alpha t. So that's how we go about getting the equations. Then you can say, okay, well, now I want to realize that omega is d theta over dt. So I can integrate omega equals omega 0 plus at over dt, and that'll give me theta equals 1 half alpha t squared plus omega 0 t plus theta 0. And again, just like we did in chapter 2, we found the kinematic equations for constant acceleration, only this time we found the rotational kinematic equations for rotationally constant acceleration. Uh, then we're going to talk about torque in section 10.4. Then we're going to talk about in 10.5 rotational dynamics, specifically torque and rotational inertia. This is where we're going to actually learn a more formal version of Newton's second law for rotation. 10.6 is solving problems in rotational dynamics. 10.7 is determining moment of inertia. That's where we're going to do the integrals that you can expect from me. And then 10.8 is going to be the rotational kinetic energy. 10.9 is going to be rotational plus translational motion, i.e. rolling. And then 10.10 is an asterisk section. That means it's optional. And it's going to say, why does a rolling sphere slow down? And basically, again, I tried to strip all the homeworks and the practice tests of those types of questions because I'm not going to test you on them, but there may be some you run into, but you're not responsible for it for the test. Any questions on that before I move along? I've only got about 15 minutes left. All right, and always you want to read the chapter opening question, ponder a solution or an answer to it, and then use that as a focal point while you're reading along to look for the right answer, and that'll keep you sort of motivated and attentive to the test to the text as you're reading it. So now I'm going on to angular quantities in section 10.1, and I've sort of talked about all this already. I should point out that 2 pi, let me write this in red. So 2 pi radians is equal to 360 degrees, but it's also equal to 1 revolution. And it's also equal to 1 cycle. Those are sort of things that we use interchangeably. I should also mention that 1 arc second or 1 arc minute is equal to 1/60th of a degree, which also means that 60 arc minutes is equal to 1 degree. Similarly, 60 arc seconds with 2 marks is equal to 1 arc minute. So those are some conversion factors that you'll sort of need. Hopefully you already know the radians one. That can also be broken down to pi radians is equal to 180 degrees. And I should mention, since S is equal to R times theta, if you solve for theta, you get S over R. S is supposed to have like units of meters, and then whatever unit S has, R should have that too. So S over R is truly a pure number. Therefore, theta is a pure number, and radian's not really a unit. It's a pure number. That's why you'll see in many equations, we'll just throw away the radian or just gen one up at any time because the radian's not truly a unit. It's just uh, a it's basically a non-denominate number, and you can throw the units on there for convenience and take them off for convenience as well. So now that I have that, let's look at example 10.1. Example 10.1 says a bike wheel rotates 4.50 revolutions. How many rotations has it, how many radians has it rotated? So theta, notice how I'm trying to get you guys to associate a particular symbol with a particular number. In this case, he said 4.50 revolutions. That's a measure of how much turning has happened. So I'm going to say theta is equal to 4.50 revolutions. And you say theta equals question mark radians. That's really the question. How many radians is that? So solution, what we know is one revolution is equal to 2 pi radians. So we're going to say 4.50. We're going to put that over 1 like we normally do when we're converting units. Revolutions. Now I'm going to multiply by 1 such that the units I have disappear and the units I want remain. So that tells me I'm going to put the 1 revolution in the bottom so that it can cancel out with the revolution in the top. And that means I'm going to put the 2 pi radians on the top, and you can see that the revolution cancels out with the revolution, and you're going to get, in fact, 9 pi. Oops. 4.5 times 2 is 9, so this is going to be 9 pi radians. But that also could be 9 times 3.14159 gives me about 28.27 radians. So both of those are correct answers. I usually find it more convenient to talk about my radians in terms of pi as opposed to in terms of just radian numbers. But either way, that's good enough. Any questions on that? All right, I think we got time for another one. Let's do example 10.2. This says birds of prey in radians. A particular bird's eye can just distinguish objects that subtend an angle no smaller than about 3 times 10 to the negative fourth. A, how many degrees is this? And B, how small an object can the bird just distinguish when flying at a height of 100 meters? So we're going to say delta theta is 3 times 10 to the negative fourth radians. A, delta theta equals question mark degrees. And then B, if 100 meters away, how small of an object is discernible? Okay, so that's what they're asking here. Now, solution, we know pi radians is equal to 180 degrees. That's one way of doing it. Now, we also have some information that S is equal to R times theta that we can make use of. You're not necessarily going to see how to use that yet, but you will in a second. So for starters, for part A, we're going to say 3 times 10 to the negative fourth radians over 1 times pi radians in the bottom, 180 degrees on the top. So I'm going to say 3 times 10 to the negative 4 times 180, and then I'm going to divide that by pi, 3.14159, and that gives me 0.01719 degrees. Now, we only had one sig fig, so technically the 7, the 1, and the 9 are not sig figs, but that gives us roughly what delta theta is in degrees. Okay. Now, what we're talking about here is a bird of prey like a hawk or an eagle or something like that. And they do have really nice, what we call angular resolution, the ability of the eye to discern two objects as two separate objects instead of one. If you've ever driven, like, or even rode on the road late at night on a long straight road, when you first see a car way up in the distance coming to you, you can't tell whether that is a car or a motorcycle because for a period of time, you just see a single white dot. And then if it gets closer, if it's actually a car, it'll turn into two separate dots. But if it's a motorcycle or if it's a car with one headlight, it'll continue staying one dot. Okay. But what happened was once it became discernible as two separate lights, that meant the angle between the left light and the right light was within your angular resolution. So you had a delta theta that was comparable to what you could see. And if I remember correctly, I think the human eye is normally on the order of a half a degree is what it can discern. Which is way, way smaller than, way, way bigger than this 3 times 10 to the negative fourth, because we're looking at 0.01 degrees, so 1/100th of a degree. And I think that that might be about right. It's like a half a degree. I don't think it's an arc minute or an arc second or anything like that, but it's definitely more like on the order of a half a degree. So now, how are we going to use that? Well, what you want to realize is if you have a bird flying and they look down, okay, then what's going on is this bird is looking, and this angle right here is delta theta. And if the angle is delta theta 3 times 10 to the negative fourth radians or smaller, then it can tell the back end and the front end of this animal. So maybe this is a cute little bunny rabbit that the bird is getting ready to meet and have a good day with. Okay. So what you can look at is you can realize that this is about 100 meters and that S is equal to R times delta theta. Now, S is that arc length, whereas the actual chord length is what we want to know far as the size of the bunny rabbit or whatever. But you can see if that angle is really small, then this chord length is really close to the arc length. So that's what we're going to say. We're going to say chord length is approximately equal to arc length for delta theta small. So what we can do is say S is equal to 100 meters times, I need this to be in radians, so it's going to be 3 times 10 to the negative fourth radians. And of course, that gives me 3 times 10 to the negative 2 meters. Notice how I just dropped radians, but radian wasn't really a measure anyways. It was meters per meter or centimeter per meter per centimeter or something like that. So what we have is in fact about 3.0 centimeters. So even at 100 meters, which is comparable to a football field, you can see something that's 3 centimeters, which would be about that big. An eagle could tell the head from the tail of this object that's only 3 centimeters long like that, even across the distance of a football field. That's pretty impressive. Anybody have any questions on that one? All right. Well, that's it. I think we've done enough, and you guys are free to go. I'll wait here for the last person to leave in case anybody has any questions. Remember, I'm still working on your test. I've got probably 5 or 6 more students left to do. I'm hoping I can get them done tonight. I'll send you an email when I do get them done. If something comes up and I don't get them done tonight, I'll do them tomorrow morning before 9. But either way, when I'm done, I'll send you an email. because I have an email that I want to send you that explains how I grade it and all that good stuff. You guys have a good evening. Contact me if you need anything, and I'll wait here till the last person leaves. Thanks for coming. Do you have a question, Cameron? Right. Guess not. All right. Well, have a good evening. Bye, everybody.